All right, this video is to talk about the superposition principle, and I'll also show a brief introduction to wave interference. Lost my screen there for a second. Give me just a second. There we go. We're back. Okay, so let's get to it. The superposition principle states that the total shape of a wave on a string, I'm going to be talking about a wave on a string in this example, but this is true for all waves. So the total shape of the string is equal to the shape of the first wave plus the shape of the second wave. And that could be a sinusoidal wave or a pulse. For example, the total shape of the wave on the string, we could model this as one equation, right? This would be y1. We could have another pulse, y2, and I'll have an animation in a second, and that gives me the total shape. This seems really obvious, but there are some limitations or cases where it turns out the superposition principle does not apply. We generally ignore these in first-year physics, but I want to mention them very briefly. If your string wave has too large of a deformation, sometimes the string tension will get a little bit wonky, and then the tension in the string is not, it's changing as the wave travels. That's something different. Or if the slope of the pulses gets above 10 degrees, so the pulses I was actually using earlier probably were not modeled very well by the superposition principle, maybe only approximately. But basically the derivation that's discussed here, I believe on page 29 of volume 3, used the small angle approximation. So yeah, strictly speaking, if you want to get really precise results, the superposition principle will not always hold, and you'll have to do something else. You can learn about that in a graduate level course or something. Water waves. If the height of the wave is negligible compared to the water depth, like a wave in the deep ocean, right? The wave might be 10 meters tall, but the ocean could be thousands of meters deep. Okay. A sound wave, right? If you make a sound wave, there's pressure associated with the molecules smashing into each other, and those pressure changes have to be negligible compared to the atmospheric pressure. Sometimes you'll hear me call it an overpressure, right? So when I shout, the air molecules get crammed together, and the pressure is slightly above atmospheric. It's slightly overpressured. More on that in the next chapter. And electromagnetic waves, if the energy density is too small to create particle antimatter pairs. So, right, basically, we need these things to be true for the superposition principle to apply. You're not really going to need to know that, but I just thought I'd mention it in case you were curious. Let's get to a simulation really quick. Bring it up. And I'll put a link to this simulation here in the comments after I finish this video. All right, so this is me trying to simulate what we were just talking about. All right, and let me just label it here. We're going to have this pulse is going to be traveling this way. We've got this other pulse traveling this way. And what's going to happen when they meet? So give me just a second. I'm going to start running this thing. If I run this. So the question, right, when they line up with each other, what's going to happen? What will the shape of the wave look like? Just think to yourself what it will be. Pause the video, think what it'll look like, and then I'll hit run and you can see what it looks like. I'll run this okay, so I'm about to run the video. Last chance. Here we go. Let's watch what happens to the shape. And maybe I'll mention two things before we do that. Notice that this height here is 3. And this height over here on this other one, whoops, the purple one, this height here is 1 meter. So we've got a 1 meter pulse plus a 3 meter pulse. I should label that. Or maybe this is centimeters. I don't know. Who cares? And these could be 2 water waves meeting in the ocean or something. All right, so let's go ahead and run it. We see that the 2 pulses are going to add together. And notice the total pulse height, when they're right on top of each other, The total height is about 4 meters here. So that's what I was saying about the superposition principle. All right, so I'm going to go ahead and keep running this now. Whoops, there we go. Let's speed this up a little bit. And maybe I'll start it over just so you can watch. Here we go. And notice the two pulses pass right through each other. Okay, and what if one of them is negative? Let's reset this. All right, so now I suppose I should fix my annotations. Let's just clear them all off. I'm going to run this video. If you want, pause the video and see what you think the shape will look like when they overlap in the middle. So I'm going to run this simulation. They're coming towards each other. What is this going to look like when the two pulses overlap? Last chance. Okay, here we go. Ooh, now I'm going to just step this back. I can actually control the time with this slider at the front. So let's just walk this through. They're getting closer together, closer together, closer together, closer together. And now the downwards wave pulse is partially being canceled by the upwards wave pulse. And notice right about here, whoops. Let's run this. Right about there, hopefully you noticed, right? We have +1 for this height. We have -3 for this height. And when you combine these two, we get a height of, what was it, about 2? So this works with negative pulse heights as well. All right, and we'll do some more examples, worked examples in class, and we'll also talk about sinusoidal waves in just a minute. But that's a brief introduction to the superposition principle. And let's keep in mind there are limitations to this, but for our class, we're pretty much going to ignore them.